Welcome, everyone. This session is for data scientists and AI developers that are looking to customize models and deploy at scale to build high-quality and cost-effective agentic applications. So let's get started. We are seeing two big trends in the market, in the industry. First, we are seeing rapid adoption of agentic AI in enterprise software apps. This adoption is expected to grow to 33% by 2028, from 1% in 2024 to 33% by 2028. That's a 33x increase in just 4 years. To build these agentic applications, you need models that are high quality, cost-effective, and fast. And customers are increasingly relying on open-weight models to build out these applications. Despite huge opportunity and clear line of sight on how to build these applications, we continue to see that majority of applications never reach production. Let's take a look at what are the key challenges that customers face which leads to these failures. First, customers lack standardized tools to customize models with different techniques. So they end up spending time building out these workflows, standardized tools, which delays the time to customize the models. Once the models are customized, you need an inference stack to host these models with the right price-performance ratio. It takes a lot of effort to find the right instance, right container configuration, constantly adapt new inference optimization techniques that are coming in to ensure that your inference stack is meeting the latest requirements, which is complex and requires a ton of effort, which further delays the timelines for these projects. After the model is deployed, customers need tools to track the behavior of these models and the agents. Often, the observability is fragmented across two different tools, which makes root causing and debugging of the behavior much harder, further delaying any progress. And then once you identify all these issues, now it's time to take your model customization workflow into production. And often the experimentation work is done with glue code, which doesn't scale well when you try to deploy that to production. So often these pipelines need to be rebuilt. And this disconnect leads to further delays. And lastly, to deploy these models at an enterprise scale, you need the right governance practices. You need capabilities to track, audit, and version your models, generative AI assets, so that you can ensure as they move from dev to staging to production environments, you can keep right track and ensure they meet compliance and governance requirements before they can be deployed to the customers. I'm Amit Modi, Senior Manager for SageMaker Model Operations and Inference, and I have with me Dan, who is our worldwide specialist for GenAI, and Ying, who is the co-creator of SGLang. In this session, we'll do a quick overview of all the SageMaker capabilities that can help you address some of these challenges. Then Dan will do a demo that will bring all these capabilities to life. And then Ying will talk about some of the key highlights for SGLang that helps you host cost-optimized inference at scale. So let's dive in. SageMaker offers capabilities to train and fine-tune these models. SageMaker offers the broadest selection of models, all popular open source models, as well as Amazon Nova models that you can use to get started. They meet all the enterprise requirements. We've already gone through the security scanning and so on, so you can quickly get started. You can choose from the broadest range of recipes to fine-tune your model and customize them. We'll take a little bit of a deeper dive into these recipes in coming slides. And you can also choose from the right training infrastructure to train these models, whether you want ephemeral compute with fully managed training jobs, or you can have persistent clusters to run large-scale jobs with SageMaker Hyperpod. SageMaker has built-in resiliency into these infrastructure, which helps you train your models faster. Let's take a look at some of the key capabilities of training. So the first key capability that SageMaker offers is when you kick off these training jobs in Hyperpod, it constantly checkpoints these jobs. So in case there is a node failure on the cluster self-heals by replacing with a good node, and then resumes the training job from the last checkpoint. So your work is never lost. And it also accelerates the training because there are multiple node failures that happen during the day. The self-healing cluster takes away the burden from you to identify those nodes, replace them, resume the job from the last checkpoint. All of this is taken care of you as a managed capability. The another key capability is these fine-tuning recipes. So SageMaker offers fine-tuning recipes to customize your model for most commonly used popular models and for most common techniques. You can get started by putting your data, training and validation data into the right directories, identify the right recipe for you for your use case, and then kick off the recipe either on the fully managed training jobs or on the hyperpod clusters, depending on your compute requirements. Next, let's take a look at SageMaker AI inference. We talked about the key challenge with inference was to host cost-effective inference. You need capabilities so that you can deploy your models faster, quickly. SageMaker AI inference offers capabilities that allow you to deploy open source or fine-tuned models with a couple of steps onto a managed instance, either through UI or through SDK. You can choose to host any model on any framework, on any different type of infrastructure to make sure you're getting the best performance. SageMaker out of the box offers high throughput and low latency for your endpoints. And we'll take a little bit of deeper dive into some of these features. With SageMaker, you can deploy multiple models onto the same endpoint. This ensures that you can scale the one endpoint to all your use cases to drive the maximum utilization out of GPUs. The intelligent routing built into the endpoint redirects the request to the right model and ensures there is no performance penalty. You can scale up to hundreds of models on the same endpoint depending on the memory requirements. SageMaker also emits metrics for each of these models. So you can configure auto-scaling policies for each model separately. This allows your SageMaker inference endpoint to auto-scale as the traffic grows. In this use case, you can see the foundation model 3 has high traffic, and it can auto-scale only for the foundation model 3 and make sure it meets the requirements. Next, we recently launched a capability that also allows you to get better throughput out of these models. The expectation for customer for inference is that they need fast inference and fast response. In reality, these LLMs generate one token at a time, which makes it really hard to meet the customer expectation. We launched speculative decoding recently. Speculative decoding works this way. So you have a foundation model, and you have a draft model. The draft model is a smaller model that does predictions for the prompt, and the foundation model validates these predictions with calculating some probabilities. It accepts some of the tokens and rejects the rest. This is a simplistic view of how this works. In reality, you can have draft model actually produce out multiple variations that foundation models can choose from. So let's take a quick look at an example. In this case, the foundation model and the draft model get the prompt. The draft model produces the next set of tokens. Foundation model decides what is the probability for each token and accepts some of these tokens. And this is how speculative decoding occurs. This leads to latency reduction and up to 2.5x higher throughput for your model without compromising on the accuracy. And all these capabilities work out of the box. So the way it works is you bring your own data set, which maps to your traffic patterns, and use that data set to fine-tune the draft model. So the draft model can do better predictions. SageMaker kicks off an asynchronous training job to fine-tune your draft model. After the draft model is fine-tuned, you can look at the evaluation metrics, choose to deploy that on the same SageMaker endpoint without provisioning a new instance, and then the speculative decoding gets started. Out of the box, SageMaker offers managed containers to host more popular frameworks like VLLM or SGLang. SageMaker offers open source containers with deep learning containers, which offer these two flavors of most common frameworks, or using a proprietary LMI container that also offers TensorRT LLM. Today, we also announced the launch of serverless MLflow on SageMaker. With serverless MLflow, it's fully managed experience. So you don't need to worry about managing any infrastructure, and it's all serverless, so it scales up and down based on your requirements for when you are running a large-scale training job or you are sending out the agent traffic. We'll talk about those use cases in a bit. You can log your experiments run, evaluation results, or agent traces all in one place. And serverless MLflow is free. It does not have any additional charges. So here is a screenshot of how the experiment tracking works with MLflow. You can see within an experiment all the runs, which is basically each training run. You can compare and contrast the training run to identify the best candidate model that you want to take to production. So you have all the observability from the time of model customization. If you're using agent core for deploying your agents and SageMaker AI for customizing the models, Agent Core already emits all the traces into Agent Core observability dashboards, and you can also send them to MLflow because they meet the OTel requirements or the OpenTelemetry specifications. SageMaker also offers partner AI apps as 1P capabilities, which are third-party apps that can also help you monitor agents as well as the model performance. So now let's take a look at how this works. You can now see on the left side, there's a complete trace tree, starting with the invoke agent at the top, drilling down through the workflow build process, capturing each step of the LangChain operations, and even showing the tool calls. And you can see multiple assistant interactions too. This hierarchical view gives you the complete visibility into every step of the agent, including the conditional branches and iterations, which makes it easy to root cause any issues within the agents, and you can go down to the model customization and see which model was used, what data set was used, which makes debugging much more easier. Now that you have your experimental workflows figured out, you have all your observability in one place, you need capabilities to productionize all these experimental workflows into scalable and repeatable workflows. SageMaker AI offers pipelines. You can simply convert your existing experimental code into pipeline steps by annotating with a @step annotator in code, or drag drop all of these steps into a UI to create an end-to-end pipeline. SageMaker also offers built-in steps for training, evaluation, and deployment that eliminates the need for you to write any redundant wrapper code for spinning up the training jobs and any infrastructure. And pipelines is all serverless orchestration, so you don't need to manage any infrastructure. We emit all the telemetry to CloudWatch, where you can observe the behavior of each pipeline step. SageMaker pipelines also have caching built in it. So if a pipeline fails and you re-trigger the pipeline, it will skip the steps that were already successfully executed. Lastly, for governance, we talked about how you need to keep track of and manage each version of the generative AI assets. So SageMaker offers model registry, which is the single source of truth for all your model versions. SageMaker AI model registry is a central hub to manage the entire life cycle of the machine learning models. We'll take a look into some of those key capabilities in a moment. You can track all the metadata corresponding to the training jobs, evaluation runs, and so on into SageMaker model registry. So here, with SageMaker model registry, you can set up cross-account access that allows you to track all the models in all your environments in one place. So you can track not only the environment that you're working in, but also your staging and the production environments. Model registry also enables you to capture all the details of the training job, so you can have end-to-end lineage of what the model went through, which makes it much more easier to debug in case you run into any issues. Next, I will hand it over to Dan, who will walk us through the demo to bring all these capabilities to life. Thank you.
Hello, everyone. Today we're going to be going through this demo, which showcases a lot of the capabilities that Amit was talking about. Let's imagine that we are some kind of clinical healthcare provider, maybe a clinic or possibly an emergency room, and we want to accelerate the amount of people that we can see. And we want to do this using machine learning, artificial intelligence. So what we're going to do is increase the amount of patients we can see by developing some kind of agent using a lot of the techniques that Amit had mentioned. We're going to start by hosting a language model onto a SageMaker managed endpoint. We're going to fine-tune it, and we're going to orchestrate that entire process using SageMaker pipelines. We're going to make some friends along the way. We're going to incorporate ML flow for observability and tracing. And then we're going to deploy that model onto not just a managed endpoint, but we're going to log it inside a model registry. We'll look at SageMaker's model registry, as well as ML Flow's model registry, and how we can incorporate governance considerations like a model card in both of them. Then once our endpoint is hosted and up and running, we'll examine how we can connect that endpoint to something like an agent. We'll start with an agent that's built off Strands SDK. If anyone's never worked with Strands SDK, it's a very lightweight capability, a lightweight open source tool that lets you build agents very quickly. We'll also examine how you use native MCP and connect all of this with some of the capabilities within Bedrock Agent Core. Another thing we're going to do that's a little interesting is take advantage of SageMaker's bring your own container paradigm. We're going to use a new repository called ML Container Creator. The QR code links to that if you wanted to take a look at it. It's a very, very new, just launched like 2 weeks ago, open source repository. So if any of you are interested in contributing to the open source world, this is a great place to get started because it is very new. So without further ado, let's take a look at this first part of launching our model. This is the part of the architecture that we're going to be focusing on in this first part of the demo, where we're going to be training a Llama 3.2 3B instruct model using QLoRa adaptation. And we're going to host it on a SageMaker endpoint using SGLang for serving. So the SGLang container that we're using is actually one that we're bringing ourselves. We're building it ourselves using some of the assets generated by the ML Container Creator repository. So let's dive into how this actually works. The first part of any notebook is a big list of imports. Don't really bother yourself with too many of these except for these steps. These are the pipeline definition files that we're importing from our file system that tell us how to execute each part of the pipeline. And we'll see in a moment how they come together to form a directed acyclic graph, kind of like what Amit had shown on the slides before. Each one of these has special instructions about how each step is supposed to run. The inputs of one step get processed and become the inputs to the next step, or the outputs of the first step become inputs to the next step. And I'll take a look, I'll show you what one of these steps looks like in a moment. As we continue, we're basically setting up the rest of our environments so that we have a couple of Boto 3 clients that we can work with, a fancy timer for keeping track of things. Where this really gets interesting is where we initialize our ML flow environment for this demo. We need to give our code a direction or a place to point all of its telemetry requests, all of its parameters and metrics that we want to log through each of these pipeline steps. So what we're actually doing here is we're capturing the ML flow ARN. This is using a server-bound ML flow instance, but now with serverless, you can do the same thing. And we're setting the tracking URI and experiment name in our environment. And these two lines of code, you'll see them in the steps. They're included here for completeness, but they're actually used in the steps where we're publishing metrics and logs and configuration items to ML flow within each pipeline step. So this is where we set these up, and you'll see it more in each step as we look through those. Then we continue to identify where we're getting our configuration, our container assets from. I took the liberty of using ML Container Creator to generate an SGLang container, and then I uploaded those files to S3. It's really just a Docker file, a couple of serving file, basically spins up an SGLang server onto whatever instance you deploy it on. So I've put all of those onto S3 already, and we're going to define where we're creating that inside Elastic Container Registry, because we're creating our own container and deploying it onto a SageMaker endpoint. And we're going to be using Llama 3.2 3B instruct for this fine-tuning job. So this is the model ID. We're going to get it directly off of Hugging Face inside our fine-tuning job. This was my Hugging Face key. And this wall of text is the pipeline definition. So each one of these blocks is effectively a method call to the files that we imported at the very beginning. I'm not going to spend too much time on this, because if you haven't worked with pipelines before, you're not really going to appreciate this big wall of text like you would appreciate this diagram. This is the directed acyclic graph that is generated by the big wall of text that we just saw. And effectively, it's starting with building our container, pre-processing a data set for fine-tuning. That data set is the Freedom Intelligence data set, Freedom Intelligence Medical Reasoning 01 data set. It's effectively a series of questions and answers using chain of thought reasoning that we're going to use to fine-tune our model to become a better clinical advisor. So we're going to pre-process that to work for our Llama model. We're going to do QLoRa adaptation on it, and then we're going to deploy it using our custom SGLang container. We're also going to register this inside SageMaker model registry and the MLflow model registry. So all of this stuff these steps are represented and defined in these method calls. We stitch them together using a SageMaker pipeline object, and you can see the steps that we've imported earlier on. And we upsert the existing role. Now, this role is permission to do all of the things we needed to do within each part of the pipeline. And the magic happens when we run pipeline.start. This initializes a pipeline run. This creates the pipeline if it hasn't been created for the first time. I'm sorry, that's already been created. This executes a new pipeline run. And once it's successful, because it eventually will be successful, each of these steps will show a green tick mark. And then you can kind of double click onto each of these and take a look at what has happened. It'll point you to the CloudWatch logs, other parameters for each pipeline step. And this is how it looks within SageMaker. We can go into the console now and take a look at all of my failed runs and my one successful run. Or we can look at how this looks in MLflow. MLflow has a very similar layout. Instead of a graph, we have this list of pipeline steps that have run under a run ID. And you can see the BYOC container, data preprocessing, QLoRa adaptation, SGLang server model registration. All of the same steps are also logged in MLflow. So let's look at one of these steps to see how this was set up. I'm going to pull out the QLoRa fine-tuning orchestration step. Each of these steps is about the same. The only difference is what's actually happening, what you're actually instructing the training job to do. In this step, we're instructing the training job to fine-tune the model, but every training step is going to have, or every pipeline step is going to have some of the same elements. We're going to have an @step annotation. This allows us to define a step separately from our notebook or from our pipeline context so that you don't have lots and lots of very long methods in the same file. You can import them the way we showed before, as long as you define a set of requirements, because what you're doing is you're creating a training job and you're executing this code inside that SageMaker training job. We're also passing information about the MLflow tracking server. This allows this step to publish metrics and telemetry data back to MLflow. Then some of the things you'd come to expect from a fine-tuning job: training data set, test data set, the model ID that we're actually training. In this scenario, I'm using my Hugging Face. We're pulling this straight from Hugging Face. So we have a Hugging Face token that we're passing and a role. Here again, we see we're setting the tracking URI and the experiment name, just like we showed before in the previous notebook. This is how the execution context knows how to publish metrics and log data to MLflow. Then we define the MLflow context. We're also setting up automatic system metrics logging. This captures system metrics like memory used, disk used, network bytes I/O, and we're setting up the ML flow context, and we begin running the job. And this is all the kinds of this is where we would set up our training configuration, and you can see eventually as we get down to the end, we're going to kick off a training job. We're defining our compute, input data, and eventually a model trainer before we actually call train. Now, all of the things that are happening before that are logs, pieces of information being sent out to ML flow to make it easier to understand what has happened in this run. We can take a look at some of the system metrics for the fine-tuning job. We can take a look at some of the metrics that are published and tagged. So these are the kinds of things that you'll see when you're writing these steps for your SageMaker pipeline. This is where it's going to end up. So now that we've defined our pipeline, let's actually, I forgot to mention, this is the model card that was set up in the model registration step. This is an important piece to make note of because this is a medical scenario where an AI agent is advising healthcare professionals, and so a model card should have something similar to this, not exactly this, but similar to this when you're implementing appropriate governance standards. So we'll test the endpoint. I have set up this endpoint a while ago. That's why I'm hard-coding the endpoint name and inference component. And then we just create a standard predictor like you would with the SageMaker SDK. And we will run a basic prompt against this endpoint. You're going to see this prompt a lot. 45-year-old male with fever and cough. Temperature is 101.3 and heart rate is 98. Give me a treatment recommendation and a report. Upload the report to S3 when done. Now, this is just a simple model that's deployed onto an SGLang endpoint. Doesn't have tools capabilities. It's just been fine-tuned. So we know that the model should have the ability to perform some basic medical reasoning because of the fine-tuning job, but it's not enabled with tools to upload a report to S3 yet. So this is the output here. We can see that the patient details have been set up in a nice report style format, some kind of basic markdown syntax. And the model did a fairly good job. It's doing performing a preliminary assessment of the patient's symptoms to suggest that, that the patient is exhibiting signs of pneumonia or something similar. So this is the first part of our pipeline. The model is deployed onto an endpoint. It's using the BYOC container for SGLang that we built ourselves. We fine-tuned it, and we have tracked our entire experiment with ML flow, and we can go back and take another look at it if we want to. Our model card is registered and logged, and I will show you the model registry as well. Within ML flow, that shows you more information about the model and where it lives. Version 1. So if you do this again and you publish a new version of that model, it'll be added to the version list. The model card might get updated, etc. So this is the first part of our demo, right? We've successfully deployed a fine-tuned agent or a fine-tuned model to SageMaker. Let's give it some more capabilities. Let's build out an agent that can do take some of the actions that we were talking about, like uploading the initial diagnostic report to S3 for a clinician to review at a later time. We might also want to give it some additional capabilities around patient lookups. If a patient's already been there before, how does the model understand, how does the agent know who this patient is? Maybe there's a patient database that we can query to get more information about that patient. And so really what we're building out is this piece down here. We're going to be using Bedrock Agent Core to deploy a Strands agent onto the Agent Core runtime. The strands agent is something we're going to be building out inside this notebook. It's going to be a pretty large block of code. I'm going to walk you guys through what that looks like. And then we're going to use agent core telemetry to capture telemetry data about each request that the agent is handling. So agent core telemetry kind of complementing ML flow for observability. Again, we have this big, long list of imports. Nothing really to pay too much attention to here. Same kind of environment setup. And what I've done is I've copied the endpoint listing inside SageMaker. This is the endpoint that's been deployed, the name and the inference component that we're working on. I forgot to mention, this model is deployed on an inference component, so it scales independent of the infrastructure, so long as there is capacity on that infrastructure to scale. So we define the endpoint name and the inference component. I hard code them for the sake of this demo. And now we're going to build out the strand agent. The strand agent is an F string in Python, so we're basically injecting variables inside this F string so that it's, instead of kind of flipping between different files, just easier for demo purposes. So you can see we're passing in the region, the endpoint name, an S3 bucket for artifacts, and the inference component is in here as well. We've defined a patient data class, basically some data information about who the patient is, what kind of symptoms they have. You can imagine that this might be analogous to a record in a patient database. I'm not a healthcare professional, so I have no idea what you might find in a patient database, but I took a stab at what it might look like, and this is what we came up with. And I'm going to skip to the more interesting part, where we are. Here we go. We are invoking the SageMaker endpoint that we defined earlier. This is written inside of a method called invoke SageMaker endpoint async. This method invokes the SageMaker endpoint that we deployed earlier, but there's a couple of other things that are happening here. First, we're defining our prompt, and the prompt is basically that same query that I showed you guys earlier. It's the same one we're going to be using. I'm not changing the prompt. It's a 47-year-old man with a temperature exhibiting a cough. What we're doing is wrapping this up in inside a super prompt, which basically says that this is a clinical training scenario. What would you do in this situation as a clinical healthcare provider? Once we have that in place, we're going to define our tracer. Now, tracers are how agent core observability captures trace data and trace information inside your runtime. So we've hard-coded some attributes here, like the SageMaker endpoint and inference component that is servicing the request. This might be really helpful if you have an agent that's making multiple calls to several endpoints. You don't know exactly which one was called when. This is a great piece of information to keep inside a trace, as well as some of the hyperparameters like max tokens, the temperature, and what the actual prompt was. These are examples of what you might want to put in inside an agent trace. Then we define our payload. We're using the messages API. So we have a system, we have a component which is the system prompt, and we have a component which is the user prompt. Again, that wrapped up prompt of the gentleman with symptoms of pneumonia. And then we invoke our endpoint. Now, strands allows us to do this because we've defined an endpoint. This is how strands allows us to define an endpoint that we're going to use within our agent. And once we're done getting our response back from the model, we set additional information on our span object. This is the context that captures the trace. We're going to set information like the duration of the model's response, the length of the response, and additional metadata about the success of the query. So now we're going to configure this actual agent, right? All we did was define a way to query the SageMaker endpoint, which we deployed. Let's configure the actual agent using strands. Now, I've set this up to run inside a local mode and inside a agent core runtime context. Agent core runtime uses fast API. So you'll see that there's a little bit of overlap in this f-string so that we can kind of illustrate how to run this locally and how to run this on agent core runtime. Here we're defining a SageMaker AI model. This is the class that Strands SDK uses to define an agent that or an LLM hosted on a SageMaker endpoint. This was introduced in the Strands in August, I believe it was. So it's a fairly new capability, and it allows you to use language models outside of API-based providers such as Amazon Bedrock. And then we just pass over our prompt back to the model in much the same way that we just illustrated. You can see we have additional tracer information, additional examples of how to use traces, identifying some attributes on this trace, and then defining a span context within which we are performing additional executions. Now, if we're not in local mode, we're going to create the Bedrock Agent Core app. This is effectively creating a fast API server. And we're going to call the create medical agent. That's that block of code that creates the SageMaker model or SageMaker AI model object, the Strands agent. And then we define our entry point, which is, again, going to perform effectively the same task of passing a prompt over to the model. Except this code will only ever run when we deploy this onto Bedrock Agent Core. When we run this locally, which I'll show you in a moment, it's not going to execute this block. It's going to execute effectively the same logic, just run in a local context. Whoa. Zoom out. Okay. So what I do here eventually is write this big giant F string to a Python file. And now I'm going to actually run this. We're going to run this using shell magic to run the Python code using the local flag, and we're passing in the same friendly prompt that we've come to know and love. And when we run this, we're spinning up the file inside our Python runtime, and it's passing out the message back to the language model endpoint. This is exactly what the agent is going to do once it's deployed to Agent Core runtime. We're just not accessing this agent code over the runtime API yet. So what it comes back with is basically the same thing we saw earlier. Based on the clinical scenario provided, a 45-year-old male presents with fever and cough. His temperature is 101.3, suggests some kind of respiratory infection, et cetera, et cetera. So this is all running locally. Now we deploy it. Everything checks out so far. Let's use this on the Bedrock Agent Core runtime. So we're going to use something called the Bedrock Agent Core Starter Toolkit. If you've never seen this before, it's a pretty fancy wrapper around some of the AWS CLI commands or API commands you might need to run to deploy an agent core, to deploy an agent to the Agent Core runtime for the first time. Effectively, you're defining a runtime object, configuring your agent, and basically wrapping up the Python code we wrote alongside some requirements files and other runtime information. And then all we do after we've defined this runtime object is we execute the launch command. Now I'm using launch with code build. What this means is that code build is going to receive the objects that we've built out, and it's going to execute a new code build execution that effectively takes all of the information that we've built and walked through just now and builds it out and deploys it onto the runtime control plane, the Agent Core runtime control plane. Now, I'm not going to actually do this because it takes a little bit to run, but you can see what it looks like. It's walking you through all of the steps that code build takes to actually build this agent. Eventually, we'll get an ARN at the end. And that ARN lets us run or invoke the agent using the agent core runtime. So I'm going to invoke this. And when you deploy this inside agent core, you're going to see something like this. The Strands Medical Agent, no tools, when it was deployed, all the different versions that are up there, as well as the active endpoint. The active endpoint is what's capturing the telemetry data from our trace objects. The active endpoint is what's actually accruing logs. And the active endpoint is what we're actually making calls to when we invoke the agent core runtime with our prompts. So we're going to get probably the same exact response or very similar to the same response that we showed earlier. While we're waiting for that to finish, you can see an example of what some of the telemetry data looks like that we've captured inside our agent. So this is a screenshot of the observability window inside CloudWatch. When you select the observability dashboard inside of your agent's view, inside Agent Core, it's going to take you to CloudWatch, and you'll see something a lot like this. The different sessions and traces that have happened within the agent's lifetime, different layers of invocation, for example, the post request to the SageMaker endpoint, which is like the final layer of that invocation. It's superseded by an API call to the SageMaker SageMaker API, and then it's wrapped up in some other layers. And so we can kind of pull this apart at different layers to see what's happening at each layer of the invocation. We can also see the amount of load or the amount of resources consumed by the agents. So how many virtual CPU hours it's consumed, how much memory it's consumed in gigabyte hours, et cetera. And wow, this is still going. There we go. Well, it wouldn't be a demo. We'll come back to that. If I were a braver man, I'd run the same thing with Boto 3. At one point, this worked, so take a look at the output. And this is an example of what the trace might look like. This is a trace with an error, not a timeout, unfortunately. This is an error that shows us we have malformed JSON. Some of the JSON keys or maybe values don't have the right number of quotes around them, so it's going to throw an error. We fixed that, and now the entire chain runs nicely. So this is a great example of how you can use tracing to improve your, to kind of identify issues deep within your execution. Now we have a few more minutes left. We haven't actually built out any tools yet. So I'm going to go through the tools part of this, and I'm going to switch gears away from Strands into native MCP. And the reason I want to do this is to showcase the capabilities of Agent Core Gateway at the very end. Effectively, what we're doing here is building out another agent in almost exactly the same way that we did before, but instead of using Strands and the SageMaker AI model object, we're building a custom MCP server, as well as an MCP client that will make calls to the server, which has methods coded in to handle requests to the tools list and tools call endpoints of as part of the MCP protocol. So again, we have much the same initialization logic at the beginning of our notebook. We're going to be creating a Bedrock Agent Core role. This is a pretty standard policy document for a Lambda function that's going to be making calls to the Bedrock Agent Core control plane. And then we'll define our MCP server. Now this is where I want to spend a little time, and we only have 5 minutes left. So I'm going to spend some time walking through how we're implementing these two methods, tools list and tools call. Tools list prints out the list of tools that our MCP server knows how to execute, right? Patient search and save medical report. Patient search is taking in some general identifier, probably a compound key for a patient search database. In this scenario, it's just generically identifier. And it doesn't matter because I've hard-coded it to return one patient for demo purposes. And then save medical report, which takes in the content that we're trying to upload to S3, where we're uploading it to, and what kind of format. Perhaps we want to support more formats besides just Markdown. You can imagine a world where we're supporting lots of different patient portals, so we might want to support different kinds of file formats. Now we implementing, that was tools list. Tools call is taking in requests from the Lambda function and identifying which tool we're actually calling, grabbing the parameters that are passed into that request, and forwarding them on to the method itself. So in the scenario where we're calling the save medical report tool, we're extracting the arguments and passing them to the save medical report method. And the same for patient search. These methods are implemented down here. You can see patient search is just returning John Doe with a couple of basic medical history. And save medical report is basically dropping the response from the language model into a markdown object. Here it is. Whatever that content is, it's getting dropped into a markdown file and uploaded to S3. Fairly basic capability, fairly basic MCP tool call that what our model is now, where our agent will now be equipped to perform for us. So this has already been deployed to AWS Lambda, and we can now make calls to this. You can see it's all the same code that we wrote before. We deploy this is the code block that deploys the Lambda function. And then we recreate an agent. So the agent we're recreating here is effectively the same agent that we had before. It uses that F-string notation to make it a little easier to read inside of a notebook. But we're doing the same kind of idea as what we did before. Now, what makes this, when we're adding the ability for tools to be called here, is it's just searching through because it's a little hard to find everything. We're applying a little bit of determinism to our agent, telling it which tools to call in what order. We're telling it which patients have come in. The agent is receiving the initial prompt from whatever interface that we've built out, and it's calling the MCP gateway to get the patient information, perform some analysis on that patient information, and generate a report out of that. So all of this is, I'm running out of time, so I apologize. I'm going to skip to the actual report that's generated. And this is the Markdown report that's generated from this. You can see the same information that's printed out in the inside our notebook is now printed out here. I downloaded this directly from S3, so it's not something that I saved in my file system. Trust me. It's definitely downloaded from S3. And now we've enabled our model to make tool calls within the Agent Core runtime. Now, if we wanted to, we can actually extend this to not use native MCP, but to actually build a gateway. We can actually build a gateway using Agent Core. So I've already taken the liberty of doing that and registered this Lambda function as an MCP target on the gateway. If we go down to the bottom, we're using the requests API to make calls to the gateway, like list tools and call tool. We're defining our gateway URL here. And using requests, we can actually make calls to that. And this is what the output looks like. This is the JSON that comes back from the gateway using the MCP protocol. These are the tools that are supported, the patient search and generate medical report. And this is the output of calling those tools. Patient search returns patient 12345, named John Doe, etc. And this is the structured report located at this location in SageMaker, in S3. So I apologize, I went a little bit over time. I'm going to pass it over to Ying from SGLang to take us home.
Yeah, thank you for Amit and Dan for the great introduction about SageMaker AI. I'd also like to give you some insights about the underlying SGLang so that you have a better idea of how to leverage its advantage. The SGLang is a community building open source project, so the development momentum is continuous. And I'd like to talk a little bit about the last quarter roadmap of SGLang development. And there are two focuses here. First is we have spent a lot of effort recently on improving user experiences. And also we collaborating with all the open source model providers so that we aim to run all latest open models efficiently at large scale from day zero. And second, we spent a lot of recent focus on big refactoring, so to make all advanced features compatible with each other to achieving high performance and usability. So there are at least 5 major components here. PD disaggregation, that we keep improving the compatibility. Now we're adding more features that was supported in non-PD scenarios, now also in PD scenarios. And speculative decoding, we're implementing the V2 version so that it's with a better engineering design to accommodate different algorithms, speculative algorithms. And all kinds of parallelism, we're doing refactor on PP for pipeline parallelism and EP for export parallelism, so that reduce the bubble and make it more efficient. For all kinds of memory pool, the refactor work on the memory pool V2 will support different attention mechanisms, especially optimized for the hybrid attention, including linear attention, window attention, and full attention. And overlap schedule is a unique feature in SGLang that we carefully designed the schedule logic so that we overlap the CPU overhead under GPU computation, so achieve the 0 overhead in CPU. And then we are now working on making all those 5 components to be compatible with each other. And this here emphasized on how we focus on refactoring because engineering is at the core of our philosophy. Also would like to give you some highlight on other features. One of them is hierarchical KV cache. This feature it will be very useful for agentic applications that have many turns and huge cache reuse opportunities. Amit also mentioned that in previous slides. SGLang, for this feature, we utilize multiple layers of the storage to store the KV cache, including the GPU memory, CPU memory, and also the remote memory that utilizing NVMe. We support multiple backends, the DeepSeek 3FS, Mooncake, and NVIDIA Nixel. And this is one experimental result on a certain workload that we can see it achieves a much better latency and also much higher throughput because within this feature, we achieve much higher cache hit rate. Another highlight, speculative decoding V2. Amit also mentioned before that this speculative decoding is a very powerful optimization, especially for online serving when you have a very small batch size. It can give you usually 2 to 3 times speed up. And especially when we came into the reasoning models world, the reasoning model usually have tons of output tokens. And speculative decoding will be the a great way a very good way to accelerate in that case. And in V2 design, we add one more feature is that we make it compatible with the overlap schedule. So previously, the speculative decoding was implemented in a way that we iterate for one decoding step, and then the some CPU scheduling, and then another decoding step. And in this new version, we have been able to decouple further for the CPU control plan and GPU compute plan. So now we hide the CPU scheduling part under the GPU computation, and now only remain one mapping that store the value in GPU and only the pointers in CPU. So we only maintain that map. Then after each iteration, we just have a small step to store the future tensor to map to this map, and then read the future tensors from the map. This helps us reduce the overhead by further 10 to 20%. So when we came into the large-scale serving world, that's also always the focus of SGLang, and we have been deployed in production serving scenarios for really very large scale. So prefill decode disaggregation and wide expert parallelism are two core features that have been used, especially for the DeepSeek use cases. Separate prefill and decode engines can help us to achieve better specialization for prefill phase and the decode phase. And also we can have a better latency control. And those, for the expert parallelism, use a large degree of the EP we can increase the concurrency and the throughput. And then the result is in the first half of this year, we have been the first open source framework to match the official DeepSeek results. And this is a demo so that we can have the deployment for the prefill with a different parallelism strategy, with one parallelism strategy and the decode with a different parallelism strategy, and within the KB transfer engine in between. So moving forward, we also have further optimized this large-scale deployment on new hardware, especially so that we go into the next slide, that we came into the new world of the rack-scale Blackwell GPU deployments. In the future of inference will be at rack scale, such as the GB200 NVL72. So previously, it's like we deployed a model on one node for 8 GPUs, but now we have the 72 GPUs in one rack that are connected by NVLink. So that enables us to do more optimization for the really large scale PDN, especially the EP expert parallelism. As SGLang optimizes it, then with prefill decode, like the PD target we mentioned, and also the wide expert parallelism, we think by utilizing the new features, new kernels for Blackwell, and also the new all-to-all communication kernels. And this is one result we published in summer that shows how much performance gain we have for the GB200. We're now also working on the GB300. So that will be, I think that I can just summarize here for those highlight features. And some of the features are still in experimental status, so they are not always turned on by default. So if I always encourage you to go to our documentation website to see what's the most recent updates and the guides to turn on those optimizations. Yeah, and the last thing is last month we released the component. In addition to language model, we now support image and video generation, also image in, image out. And this, we call this SGLang diffusion that accelerates this image video generation by 1.2 times generally, and sometimes in special cases could up to 6 times about. In future models, we think will be multimodal in, multimodal out, that combining in auto-regressive language models and diffusion models. And in this release, we have from this metric benchmark that we compared with the existing diffuser, Hugging Face diffuser, you can see the performance gain. And also, on the right figure, we list how those different optimization techniques can help with the performance, the throughput. And majorly, there are 2 techniques. One is the sequence parallelism, and another one is CFG parallelism. And when we combine the 2, we got even higher improvement, even better improvement. Yeah, I think that ends my part then.
Okay, so we covered a lot of ground today. I'm just going to do a quick recap of the challenges that we referred to in the very beginning. There we go. Model customization can be a time-consuming process. It can be a little expensive at times, and it may be unclear how you optimize that workflow. What we've discussed today is really meant to give you a couple of tips and tricks on how you might do that, right? Taking into consideration, I think the clicker stopped working. There we go. How we might leverage fully managed training jobs to allow you to continuously repeat these experiments over and over and optimize that way without having to manage all of the experimentation harness. We talked about how you might host SageMaker models more effectively, and Ying just went through several great stats about how SGLang is a really great model serving engine for efficient model serving and inference. End-to-end observability with managed MLflow and now managed MLflow serverless, which is, I think it's a little more cost-effective than hosted MLflow. And we talked about using SageMaker pipelines to be able to repeat these experiments over and over and over again so that you can effectively scale your experimentation. Finally, tracking and auditing and versioning models within SageMaker Model Registry, MLflow Model Registry, giving you the ability to determine exactly where you're going to focus your optimization efforts. So thank you all for attending. This is a link to the demo video. The code is not available yet on GitHub. It will be at some point soon. But this is a link to the demo video. And if you go into your app, the AWS Events app, don't forget to leave a review for this session so that we know how to improve it for next time. Thank you very much.